Lecture 18, Scheduling in Linux. So we're going to continue our discussion of commercial, as in real-world operating system scheduling, with a much more in-depth examination of what happens in Linux. And we just discussed already the classical, traditional Unix scheduling algorithm. We talked about the Windows one. I'm going to reference in this topic the traditional Unix scheduling algorithm, so it is worth taking a look at if you haven't seen that one already. So, yeah, we're here for the penguin. Now, Linux has two scheduling modes. It has real-time and non-real-time, or maybe we should call that the normal one. And it's not strictly necessary to use the real-time scheduler, and if the real-time scheduler is used, the system can still have non-real-time threads that will be scheduled according to the normal scheduling routine. We'll talk about the real-time scheduler quickly, but it's the non-real-time ones that are actually interesting for our discussion today. So the scheduler operates on scheduling classes, and there are three classes into which processes can be assigned. The slide says priorities, but I think it should say processes. So there's FIFO, round robin, and other. And so, well, first in, first out, and round robin refer to real-time threads. So the ones that are in the real-time category will go in one of those two. All of the other ones will be in the other category, right? The non-real-time threads, which makes sense. And each class is like broad, right? Because within each class, a thread may have different priorities. And unlike Windows, lower numbers indicate higher priorities, as we've previously seen. So if something is a real-time thread, it's going to be in the range 0 to 99, and the other priorities are 100 to 139. Okay, so whether it's the first in, first out, or round robin, its process or a thread is going to be in the 0 to 99 range, and the rest of them are in this 100 to 139. The first in, first out scheduler has a lot of rules. There's like quite a bit that goes into this, and rather than a wall of text on the slide, I'll try to summarize them fairly quickly. So the rules for the first in, first out scheduler are as follows. The system will interrupt a first in, first out thread if one of the following three things is true. A, another first in, first out thread of higher priority becomes ready. B, the current thread gets blocked, for example, on an I/O, or C, the current thread yields the CPU with like an intentional call to the scheduler, volunteering, if you will, to yield. If a thread is interrupted, it goes on the queue associated with its priority. And the third rule is sort of the converse of what we've just talked about, which is if a thread in the scheduling class becomes ready, and that thread has higher priority than whatever thread is currently executing, the currently executing thread is preempted in favor of the highest priority thread. If it should happen, there are two or more threads waiting at the highest priority. The one that has been waiting the longest is the one that will be chosen. Okay, so that's a lot, but the rules are hopefully relatively straightforward. The first in, first out thread that's running will only get interrupted if it has to be, and when it is, it goes in the appropriate queue. Great. The policy is really the same for round robin, except time slicing is implemented. And that just means that there is a timer interrupt that says when we have executed for a certain period of time, well, then the scheduler runs again and it decides what to do. And when that happens, the scheduler will select a real-time thread of equal or higher priority, and it could be the same one. Right? If this is the highest priority thing, it could get selected again, even though it was the one that was just interrupted. That's fine, but it could be another one of equal priority, or if something new has come up in the meantime that is of higher priority, it could certainly be that. So the difference between these is shown in this diagram. We have relative thread priorities. Instead of assigning numbers to them, they're just minimum, middle, and maximum, where B and C are equal. And with first in, first out scheduling, we'll do the thing that is the highest priority first. We're assuming none of them get blocked for IO or other reasons, but we'll do that. And then we'll choose B, and we will continue with B until it's finished, and then C, and then A. Whereas with the round-robin scheduling, we will do D, and then B, and switch between B and C here, because there's time slicing implemented, meaning that all of them at the same priority each gets a turn. So that's the key difference between the first in, first out and the round robin scheduling as far as the Linux scheduler is concerned. Now, if one of the threads in the other category is going to run, it will only happen if there are no threads in the round robin or first in, first out queues that are ready right now. So putting things in the real-time category really gives them absolute priority over the other threads that are present, which maybe you want and maybe you don't, right? There are certainly situations in which we want to give absolute priority to some threads over others, and when we do so, we want to see to it that that behavior is actually carried out, and doing this is one of the ways. But we're going to talk about the non-real-time schedulers now in some more detail. And in versions 2.4 and earlier of the kernel, it used something that resembled the traditional algorithm. That's kind of shockingly late now that I think about it, considering when 2.4 kernel and 2.6 kernels and stuff were released. And it was, well, finally replaced with a scheduling algorithm that's called the constant time scheduler, where you could say big O of 1, because it executes in constant time under all circumstances. Fair enough. This is a big improvement over the previous scheduling algorithm, which has linear characteristics, and it also worked a lot better because it supported SMP systems better. It had processor affinity, it had load balancing, and what have you. But it didn't take very long before the constant time scheduler was itself replaced. So, like, really, it didn't take long. Midway through the 2.6 branch of the kernel, a new scheduling algorithm was introduced, and it is called the completely fair scheduler. And again, you've been granted the rank of master. Okay, so why did they want to replace the traditional scheduler? I mean, I mentioned already this idea of the SMP improvements and processor affinity and stuff like that, but a couple of observations, right? Number one, it's not very good at handling large numbers of processes. It's a linear time algorithm, so its performance gets worse as more processes appear in the system. And we see more processes appearing in the system over time, right? There's more background services, there's more things that are running. Users have more programs open at the same time if they're using it as like a laptop OS or something like that. So we can't just pretend that's not happening. It's getting worse in terms of number of processes that are running concurrently. So we can't avoid thinking about that. But there were a couple of other things that made it not so suitable for symmetric multiprocessing systems, which is, number one, there was a single run queue and a associated lock, also only one lock associated with the queue, and it did not have the ability to preempt running processes very easily. So the single run queue means a task can be scheduled to run on any processor, which is advantageous for load balancing, as we talked about at least a little bit earlier on, but there's no implementation of processor affinity. So a task that's running on CPU 0 could easily be reassigned to CPU 1 and get a bunch of cache misses. And I mean, we've discussed this idea of, should there be a penalty associated with moving from one to another? It's manageable, it's doable, but we don't want to do this if we could avoid it. And the traditional scheduler had no such consideration. Another thing, of course, is that the single run queue and associated lock means that because there's one mutual exclusion construct protecting manipulation of the run queue, whenever one processor wants to modify it to either enqueue or dequeue a task, all other processors have to wait until it's unlocked, and that can take non-trivial time when we have linear operating characteristics of the algorithm. Choosing what to do may take a meaningful amount of time. During that time, that process is not able to start yet because we haven't chosen it yet, but other processors might be waiting for work to do because they're waiting their turn to choose what to do. So that's not good. That's not good at all. And preemption didn't work as expected either. Lower priority tasks would continue to execute while higher priority tasks would wait. Only something getting blocked, a time slice expiration, or an interrupt might be a trigger to cause the scheduler to reevaluate what process should then be executing. So all of those things were not very ideal for a modern symmetric multiprocessing system. So why do we talk about this? Like, why do we care about the problems? Well, I think you can see when we talk about the constant time scheduler, how it was designed as an attempt to address the issues that were observed in the traditional scheduling algorithm. And I think that informs and helps us understand why they made the decisions that they did. So let's look at that. And the constant time scheduler has two data structures for the processor in each system. The important stuff to know is we have a struct here. I mean, I don't think it's actually implemented like this, but use this as illustrative to get an understanding of it. But we have a structure called priority array, and it has an integer property in it that contains the number of tasks, so threads in this array. We have a bitmap, which represents the priority, and then we have struct list head of a queue, and this is the priority queues. So max prio is 140. It's the highest priority number, and it's also the number of queues. And so in this structure, we have an integer. We have our unsigned long that's going to be used as a bitmap, and then we have our queues, and the queues are, well, there's 140 of them, so these are just the pointers to the head of the queues. Okay, so there's one queue for each priority level, and the bitmap array is of a size to provide 1 bit per priority level. So with 140 levels and 32-bit unsigned long, could be different on your system, depends. Bitmap size is 5, but the actual implementation depends on what is the size of the unsigned long in your system, so it divides as best it can without any extra wasted space. Okay, so what we'll see is that initially, on startup, there are no tasks in any of the queues and all the bits in the bitmaps are 0. If a process or thread is created and it enters the ready queue, it's put in the queue corresponding to its priority value. So if its priority is 132, that's where it goes in the queue, although it's going to be -1 because we started at 0. Actually, no, we won't. It'll be 132 because, 0 is a priority. So 139 is the maximum. So it's 132, then it goes in at that level. And if that queue was previously empty, its bit in the bitmap is set to 1 to indicate that that queue is no longer empty. And I think at this point, you're already getting a hint as to the strategy. How does this work? And so here we have the actual real diagram that explains how it works, which is to say we have 2 copies of everything. There's active queues and expired queues. Okay, so active queues are tasks that are ready to run, and we have a bitmap, and the bitmap will show us which queues have anything in them. And then associated with the bitmap, we have the queues themselves, so we have 140 of them, each queue containing ready tasks that correspond to that priority. So that part is pretty straightforward. Right? If we have a task, we put it in there. If it gets blocked, we take it out of the queue and put it in the blocked queue for whatever it's blocked for. That's fine, right? Why do we have a second one? So we have this array for the expired tasks as well. So if a process doesn't complete its full time slice before it's preempted, then it goes back into the ready queue. And it can in the future run for the remainder of its time slice. If it does reach the end of the time slice, then it gets moved to the expired queue, right? It's used up its time slice for this round, and it has to wait. All dispatching takes place from the active queues. So we always choose from the highest priority one, so we just look at the bitmap and we find what is the earliest one that has a bit set to 1 in it. In this example, we can see it's pointed out on the slide. The highest priority queue there is, I believe it's 7. And based on that, we can go immediately to the corresponding queue, dequeue the task, and if that was the last one, set the bit to 0. Let's imagine that this task runs to completion, and it doesn't need to be put back in the queue. Great. So we can remove it from consideration. We'll go to the next one, and we'll take the next thing that's in the active queues, and we will put it to work. We will get it started on the CPU, and let's say it runs to the end of its time slice. Okay, then we move it to the expired queue. When we do that, it's taken out of the active queue and it's sitting there in the expired queue, and we will continue with the next scheduling. We'll take the next task here, it's I think 11, and at that point we will look at that, and it gets blocked on I/O, so we move it out of our active tasks right now because it's blocked on an I/O. So we wait, and then we take the next item. Eventually, we will come across a queue that has more than one item at that same priority. When that happens, we have round-robin scheduling between all of the items at the same level, and everything will get a chance to run, and eventually the active queues will be empty. Right? All the tasks have run for their time slice, and they've made it, presumably, to the end of said time slice, or they've terminated, or they're blocked on I/O. And when the active queues are empty, we just change places of the active and expired queues, and execution continues. So a task that gets to the end of the time slice goes in the expired queue. It waits there until everybody's had a turn. When everybody's had a turn, then it's time for starting again. And you can see how everything here is a constant time. We don't have to do a lot of work here to actually get the next ready task. The bitmap tells us exactly where to go, so we don't have to iterate over the active queues. So that makes it easy. We always dequeue the item that's at the front of the active queue, so we don't have to iterate over the queue contents itself, and switching the places of the active and the expired queues is as simple as swapping 2 pointers, and that's pretty much it. Right? Enqueuing an item, again, we just throw it at the back of the queue. It's pretty easy. There isn't a lot that we need to do, so everything can be done, as the name suggests, in constant time. Okay. This is a long explanation, but I hope it gives kind of a good understanding of this constant time scheduler and why it works the way that it does. Now, you're probably asking, or at least, when I get to choose what you say in this example, you're asking, okay, well, if this is how it works, why did it get replaced? Why did you talk about the completely fair scheduler? So we talked about the completely fair scheduler because, well, it doesn't necessarily provide very good performance for interactive processes, right? One of the things that we'll see is, everybody gets a turn and it moves around, to the next round. That works pretty well for a lot of things, and it's quite fair in the sense of allowing all the processes to get a chance to execute, but it isn't ideal for something where we should consider user interactivity. Because, well, as the user, I want the processes that I'm interacting with to be more responsive. I want them to get more turns. I want them to respond quicker, even at the cost of background tasks that I don't necessarily notice the performance of. So, yeah, given that we're always trying to make it the year of the Linux desktop, I just read an article that said 2022 was the year of the Linux desktop. Call me at least a little bit skeptical, but yeah, that kind of thing is an ongoing discussion. A new scheduler was needed, and it was replaced relatively quickly with the completely fair scheduler. So the completely fair scheduler is written, we can actually attribute an author here, Ingo Molnar, and it's not constant time, unfortunately. Not all of its operations are constant time execution. It uses a tree structure, in fact a red-black tree, to model the ready queue, where processes are inserted based on a linear ordering of execution time. So the leftmost group in this tree is, well, the task that has spent the least amount of time executing is the thing that we want to schedule next. So we end up like pulling a lot of stuff from the leftmost node of the tree. It makes more sense when you see it. Because a red-black tree needs to remain balanced, the access time to get the leftmost element will be log n timing, typically, although you can use caching to make the next task faster. Because if you just sort of keep a pointer to, well, this is the next one, that makes it a little easier to serve up. But that doesn't solve everything, right? If a task gets blocked, it doesn't end up in the tree again, but if it reaches the end of its time slice or gets preempted, then it has to get inserted into the tree with its new location. And that's very likely not in the same place it was taken from, which necessarily could require rebalancing the tree. And that's also a log n order operation. So that's why the completely fair scheduler, we would describe it as having log n characteristics, because, yeah, although it might be possible to get the next item more efficiently than this, the worst case scenario is we're going to have to rebalance the tree. And if that is the case, the runtime behavior on that is log n. So what we see when we visualize the tree looks something like this. And so tasks, threads, however you want to think about them, are inserted into the tree based on their runtime. And the task with the smallest value of vruntime is the one that we want to choose next. And as we go through the tree, on the diagram here from left to right, the value of vruntime gets larger. And vruntime represents virtual runtime. So it's not just the actual execution time that makes a difference. There are adjustment factors. Now, rather than using a strict rule to decide about priorities and runtime and stuff like that, the completely fair scheduler assigns a proportion of CPU processing time to each task based on its nice value. So the nice values that we saw earlier when talking about the traditional Unix scheduler, they still exist and they still matter. Right? As far as we're concerned in implementing this, right, we have to keep up the behavior of previous systems, and that included the nice factor. And a nice value, as I think we may have discussed, could be in the range of -20 to +19, where -20 indicates something that is very not nice, and +19 indicates something that is quite nice. Now, the completely fair scheduler doesn't use a particular length of time slice because different CPUs run at different speeds, and depending on the number of processes that are trying to use the CPU at the same time, choosing a fixed amount of time doesn't really make sense. What it actually does is use a target latency. And the target latency is just a time window, and with the expectation that every thread should get a chance to run at least once inside that target window. And so CPU time is then handed out based on the target latency. There are usually default and minimum values, but the target latency can increase if there are a lot of extra tasks added to the things that we need to do to make it realistic, right? If the target latency is very short and we have a lot of tasks, we know that's unrealistic. Let's not try to do something we know can't work. Okay, so as I said, the ordering of execution is really the virtual runtime. It's not just the actual runtime, but it's the runtime with an adjustment factor. And so we keep track of how much time a task has spent actually executing on the CPU. As with a lot of history keeping, there's a decay factor, so that more recent history is heavily weighted in the calculation, and less recent history is not forgotten, but it has less of an impact on our actual calculation. And for tasks that are at a normal priority level, so nice value of 0, not great, not terrible, the virtual runtime equals the physical runtime. For processes that have a positive nice value, then their vruntime will be larger than the actual runtime, right? So higher priority processes, history decays faster. Lower priority processes, history decays more slowly. And so if the process has a negative nice value, then its virtual runtime will be less than its actual runtime. This means, yes, that processes that are nice wait longer and processes that are not nice go sooner, but that's in line with our expectations, right? We expect that processes that have a higher priority should be running more often, and if they're not, something is wrong in our system, right? If it's not doing the expected behavior, I have questions, right? It makes sense. So the virtual runtime, as we saw on the earlier slide here, represents the ordering. So if thread T7 is very not nice, its actual runtime may be larger than that of, say, T8, but because the adjustment factor makes it smaller, it has the smallest value of virtual runtime. If the physical runtime is 50 seconds, process with a nice value has a virtual runtime of 50. If it's nice, the virtual runtime is larger than that. If it's not nice, the virtual runtime is smaller. So, as you can imagine, the way that this system is implemented, tasks that spend a lot of time using the CPU, so they are CPU-bound processes, they end up with, lower priority than a task that spends a lot of time waiting for I/O. That just happens naturally. A task that doesn't run very much before issuing an I/O, getting blocked for some reason, doesn't accumulate a lot of runtime and therefore doesn't accumulate a lot of vruntime. So that's expected. And a process that is user interactive in that sense will get to execute fairly quickly because it's going to be, when it's ready, at or close to the front of the list. This makes the system seem responsive to the user, which, generally speaking, users like, at least in my imagination. Another thing that is kind of noteworthy in the completely fair scheduler that's really nice is the addition of group scheduling. So we can designate a number of processes as belonging to a group, and that's very nice when a process spawns a lot of threads or creates a lot of new processes, and therefore instead of treating every thread or process completely equally, a multi-threaded program's threads can all be pooled, and the group that corresponds to that, that number of threads is equal to other processes. And within the group, the scheduler does try to treat processes fairly. This is really nice for something like a shared server that has a lot of users. If we apply this scheduling algorithm using groups, where we say a group corresponds to all of the processes and threads belonging to a user, then the system tries to ensure fairness between users. Now, listen, it's not mean. It doesn't say, listen, you can't use the CPU that's idle while other people have nothing to do. It does require the system be busy for this to make a difference, but it is still nice to allow users to be treated equally. And that way, if I'm running one thread, one task, then my CPU time is not crowded out by somebody who's running like a multi-threaded calculation that's using 50 threads because, well, all threads are treated equally. Well, yeah, I have one and they have 50. So like that, they shouldn't get 50 times more CPU than I'm getting on a server that's, say, operated by the university. That doesn't really make sense. It's not really fair. So you can see what I mean about the completely fair scheduler. It's definitely an attempt to address some of the shortcomings of the constant time scheduler, which was itself a a pretty good attempt to address a lot of the shortcomings that existed in the traditional scheduling algorithm. And so, as you can see, this is kind of ongoing, right? It's not a completely solved problem. And in fact, I'm going to reinforce that in the next topic that we talk about, which is called a decade of wasted cores.